Okay, so it's about time for us to get started. I did get your test mark. People who were in Thursday's group yesterday got their test back. Monday's group, I don't have them with me right now. I've got to run after this class. I will be in my office between about 3:30 this afternoon. So if you want to drop in and pick it up in person, no problem. Otherwise, I'll give it back to you Monday morning. So your tests are done and they're good to go. Any questions about what we got covered last day or anything else in general? No? Okay. So today we're ready to start a new chapter. And sort of the point of the pre-class question for today is to get us thinking about capacitors again. So we talked about capacitors after we talked about the electric field around planes of charge. And the capacitor was the application of the electric field around a plane of charge. So now we come back to talk about capacitors and their use in circuits. So I guess I think any electrical device you can think of is full of capacitors, okay? And maybe some that you're probably not even thinking about. I think I brought these in last time, but here's a couple of capacitors. This one's a pretty big one. It's nice and big and round. This is a smaller one. Anybody who goes on to do Physics 2055 will do capacitor labs. We don't do them in 1051, just because the labs are already pretty packed. But you'll do lots of these in 2055 if you do that. So we're going to get to talking about devices with capacitors and how we use them in circuits and what they're used for. When we talked about capacitors, kind of way back when, I said it was a device used to store potential energy, electric potential energy. Kind of an interesting question is how does it store that energy? Where is it stored? Like if you think about spring potential energy, that kind of makes sense, right? If you stretch a spring out, you can see in the coils of those springs, there's energy associated with it. But where do you see that energy in electric potential energy? It's kind of an interesting question, and we're going to come back to that. Likewise with gravitational potential energy, right? If I hold something up, it has energy, but kind of where is it?
Isn't it stored similar to like a battery in the compound?
So battery is interesting. The energy in a battery is in the chemicals of the battery. It's a chemical potential energy. No chemicals here, right? So it's interesting, right? Right? It has energy, but kind of what even the heck is energy if we think about it that far? So anyway, those are some places we're going with this. And I think I won't answer it right away because I like that people are starting to think about it a little bit. So we are coming back to it. So let's give a definition to our capacitor. A capacitor is two conducting plates. It does have to be conducting. It's not insulated plates. They each have area A. They have the same area A. If they wasn't the same area, it would be here. They're separated by a distance D. Each plate has equal and opposite charge Q and equal and opposite surface charge density sigma, which is the charge divided by the area. We know that the electric field will go from the positive plate toward the negative plate. It has a magnitude of the density divided by our constant epsilon naught, and it points from positive to negative. Maybe one thing we'll say here is you notice we're using epsilon naught, and there's nothing in between the plates of our capacitor. You know, that's just air or vacuum. There's nothing in there. That's not technically how most capacitors are made, mostly due to technological limitations. Normally you stick stuff in there, like small sheets of insulating material. Those little bits that you put in between the plates of a capacitor, that's a dielectric, and we can have electric fields in that material. The difference in our analysis is instead of using epsilon naught, that talks about electric fields in a vacuum, we use epsilon, which is electric fields in a material. We're not going to go into dielectrics in this class. It's a little bit outside of the scope that we're going to do. But if anybody's interested in kind of making devices, that would be something you'd run across. Okay, so we use capacitors in circuits. So let's start talking about a circuit diagram. So we would take a couple of wires. I brought in some wires. So you would just take some wires and you would connect them to your capacitor. We represent a capacitor as two parallel lines in a circuit diagram. So these plain things, they're just wires. We assume that our wires are perfect, no resistance associated with them. And then the two parallel lines are the capacitor. So we're going to be drawing circuit diagrams with those. When you start with a capacitor like this, you get it fresh out of the box from the manufacturer, wherever you buy it from. It is completely uncharged. There's no charge on it. So you might ask the question, how do I put a charge on a capacitor? The way you put a charge on it is you hook it up to a battery. So if we want to charge a capacitor, we would take our capacitor, we would hook it up to a couple of wires, and then the other ends of the wires would get plugged into the terminals of a battery. So a long and a short line together, that represents a battery. The long line is the positive terminal. The short line is the negative terminal. So that's our battery. We're going to use some interchangeable notation here. Sometimes we write that the potential of a battery is delta V. And sometimes we write it as epsilon, and we'll get around to calling that EMF and where that comes from. So delta V or epsilon, that's the potential of the battery. I write them pretty interchangeably, so you should get used to seeing both of them. And then our capacitor, so in our diagram, we will label this delta V or epsilon, and our capacitors will get labeled C. Good to hear? So we're basically just putting our wires on the end of the capacitor like this, and then the other end goes into the power supply, and that's how you get them charged up. Let's look at the details of how that charges, because it is a pretty interesting process. So what I've got here is sort of a picture of how this happens. So what we have is a battery. That's this thing right here. Batteries are full of chemicals, which is why you're not supposed to throw them into a fire, because they can explode and the stuff goes everywhere, the battery acid. The battery is full of chemicals. The chemicals inside the batteries undergo a chemical reaction, and that chemical reaction, the change in chemical energy, makes the charges in the battery move. So it makes it move so that a positive charge comes out of the positive terminal. It hits a wire, so that's made out of copper. It's free to move because it's a conductor. The positive charge will travel along the wire, come down here, and it will hit that conducting plate of the capacitor. So the positive charge hits this plate. Then the next thing it encounters is just dead air, so it can't go anywhere. That positive charge is stuck. You think about what happens on this lower plate. Well, this is a conductor. It has positive and negative charges. A positive charge here is going to be repelled by this positive charge. It's going to start to move away. So a positive from this lower plate will move away, come back through the wire, up into the battery, and repeat. So that's what happens in that process of charging a capacitor. It's a very fast process. Like, certainly it doesn't take a whole second. Well, I guess sometimes it could take a little longer, but it's relatively a fast process. Okay with the process? Okay, let's add a couple of notes to go with that. And that process is just going to repeat until the capacitor becomes fully charged. When it's fully charged, the potential of the capacitor is equal to the potential of the battery. So when those potentials are the same, that's when charge is not going to flow anymore. So in our circuit diagram, we would put in our battery on one side, put the positive terminal here, the negative here. So this has a potential of delta V, or we might say epsilon. Straight lines are our wires. They're connected to the two sides of the capacitor. It's over here. The charge leaves the battery, comes along, hits the top plate, piles up on the top plate, repels from the bottom plate, so the top plate ends up positive, the bottom plate ends up negative. So the charge flows from the battery to the capacitor. Until the potential difference across the battery, delta V battery, equals delta V for the capacitor. When we're there, the capacitor is fully charged. It happens on a time scale, sort of fast for our life, slow for circuits. Then if we want to have a charged up capacitor to put in a circuit, we would disconnect it from the battery and we would put it in the device that we want to have a charged capacitor in. Still good? Okay.
Will we be looking at the limits of the capacitor, or are we only gonna be looking at limits with how big the battery would be that capacitor is hooked up to?
No, the nature of the capacitor is really important, so we're going to look at that next.
Okay.
Yeah, so the battery is important and the capacitor is important. So, here's a recap of what our capacitor is again, and some pictures, including a circuit diagram. So, we know that when we want to characterize a battery, we talk about the voltage of the battery or the potential of the battery. You go to the drugstore and you buy 1.5 volt batteries. So batteries are characterized by their potential or their voltage. Capacitors are characterized by what's called capacitance. Capacitance has a symbol C. We drew that in the last slide, and it has units of farads after Michael Faraday. And farads has a symbol of an F. Those are the units of capacitance. If we want to think about our capacitor, we know we've got the two conducting plates, area A, separated by a distance D. So down here we have a side view or an edge view of our capacitor, so distance D between the plates. The diagrams that we draw, this is pure exaggeration. So the plates are much closer together compared to the size of the capacitor. Really, these should be so close that you can't even really see the distance between them. So that's how small D is compared to the size of the plates. But you can't draw sensible pictures on that, so this is what we have. We have our plates, one is positive, one is negative. So one has positive charge, one has negative charge. Means one plate has a positive charge density, plus Q over A. One plate has a negative charge density, minus Q over A. We know when we have the positive and negative plates separated, that leads to an electric field that points from the positive to the negative. Here's our electric field between the plates. We know how to calculate the electric field. So the electric field between the plates equals sigma over epsilon naught, and it points from the positive to negative. So that's something we know already. The magnitude of the electric field then is sigma over epsilon naught. Sigma is our charge density, that's charge over area. So electric field could be written as Q divided by the area times epsilon naught. We might notice here that on a charged capacitor, the total charge on the capacitor is 0, because one has plus Q and the other has minus Q. But those charges are separated, that's where the field comes from, because we push the charges apart. What else do we have? So there's our electric field. We know that if we have an electric field over a distance, we have a potential difference between the two plates. The potential difference between the two plates is delta V. That's the electric field times the distance V. Then we can fill in what we had for our electric field, sigma over A times epsilon times D. So there's an expression. Oh my goodness, that's supposed to be a Q, not a sigma. Okay, sorry, it's a little bit messy. Hopefully you can see it. So our potential difference is E times D. That's Q over A times epsilon naught times D. So I put in a sigma, we're supposed to be Q. So if you look at this equation, D is a constant for any capacitor. A is a constant, those are just the material properties. So we see that there's a relationship between the charge and the potential. So those two things have a linear relationship. So we see that Q is proportional to the potential difference across the plates. So the amount of charge on the plates is proportional to the potential across the plates. So we can say that Q is equal to the capacitance C. So the capacitance C is our constant of proportionality times delta V, where C is equal to A times epsilon naught divided by D is the capacitance. Okay, so capacitors are characterized by their physical properties. A capacitance depends on how big it is and how far apart the plates are spaced, and then to an extent what's between the plates. Okay, and we're going to deal with capacitors with vacuums between the plates. So capacitance depends on the geometry of the plates. One other thing we might toss in here, just to come back to what we were starting to think about with energy dependence. A farad is our unit for capacitance. So C is Q over delta V. A farad is charge, coulombs, divided by volts V. A volt is the same thing as a joule per coulomb, because potential is potential energy divided by charge. So a farad could also be written as coulombs squared over joules. So you can introduce energy into your units of capacitance. That tells us that capacitance does have something to do with energy, and we're going to come back to what that relationship is.
For capacitance, would the units be coulombs per meter over Newton?
A joule is newtons times meters, right? Yeah. So yeah, you could say coulombs over newtons times meters. I guess you could. Coulombs squared over newtons times meters.
Is the distance.
Yeah. Okay, all good? So, the capacitance depends on D. This is sort of an interesting application we could think of next. Anybody in a band might appreciate this one. Any musicians in the room? Yeah? Okay, awesome. Who else might like this one? People kind of do a lot on making videos on YouTube or whatever it is people make videos on. So a condenser microphone? Yeah, condenser microphone. What happens in a microphone, a condenser microphone, is it has two plates. One of them is fixed in place and the other is a variable, it's flexible. There's a constant voltage between the plates. It's hooked up to a source, there's a constant voltage. But one plate, when you sing into the microphone or talk into the microphone, we talked about how sound is a wave and there's vibrations through the air. That sound wave makes the top plate vibrate in and out. It changes the spacing between the two plates. If it changes the spacing, it changes the capacitance. The potential is constant, so if C changes, charge has to change, right? Because C is equal to Q over V. So if V is constant, C changes, Q also has to change. How does charge change? It has to move back and forth off the plates. What does it mean if charge is moving? That's a current flow. So when you sing into a condenser mic, that plate flexes back and forth, changes the capacitance, changes the charge by having the charge flow. If you're getting charge flowing in a circuit, that's what changes your voice into an electronic signal. Okay, so that's sort of how digitization works, kind of. So there is neat stuff I think is interesting. So let's see if we can do a conceptual example. The capacitor has a vacuum in the space between the conductors. That means that the equation that we just wrote down applies. If we double the amount of charge, so we're going to double Q, what happens to the capacitance C? So your choices are it can get bigger, it can get smaller, it can stay the same, or it depends on the size and shape of the capacitor. Okay, anybody want to pitch in an answer?
Increases.
Okay, I got to vote for increases. Agreement? Hesitant agreement. Okay, any disagreement? Any no ideas? Okay, so that's a great range of answers. Glad to have all of them. Why don't we write down our equation for capacitance? C equals A times epsilon naught over D. Okay, let's look at that equation. If we change the charge, what happens to that equation? Nothing. Right? A is the area, so how big was it when we made it? Epsilon naught, constant. D is the space between the plates. Doubling the charge doesn't change anything. Okay, because the capacitance only depends on the properties of the capacitor.
Sorry, so just to like clarify exactly what like capacitance is.
Yep.
It's the capacitor's ability to hold charge, or like.
I would probably be more inclined to say it's its ability to store energy.
To store energy.
Yeah.
Okay.
Yeah. So let's do some examples. The first thing I want to do is change a couple of change a value. I said a capacitor carries 12 picofarads on each plate. It carries a charge on each plate, and those charges should be 120 picocoulombs. So I'm introducing P for pico here. That's a common unit when we talk about capacitors, because capacitances are very small, and a pico means 10 to the minus 12. So 120 picocoulombs is 120 times 10 to the minus 12 coulombs. Okay, so that's going to be a new one for us. So let's find the capacitance of each of the three following capacitors. So we'll use one of the two equations and get our capacitance. Capacitor number 1, we know the charge. And we know the potential difference, delta V, equals 10 volts. So to find our capacitance, C is equal to charge divided by potential difference. 120 picocoulombs divided by 10 volts gives us 12 picofarads, or 12 times 10 to the minus 12 farads. Okay, so that first one, when we know charge and potential, that one's easy to figure out. The next one is also pretty straightforward to figure out. We have square plates, 50 millimeters, that's the length of each side. So the length of each side is 0.05 meters. They're separated, that's our plate separation D, by 1 millimeter. 1 times 10 to the minus 3 meters. We want to find the capacitance. Let's write down our expression for capacitance, as it depends on the size and shape of the size and area of the plates, separation. A epsilon naught over D. Area, since they're squared, is just going to be L squared. And that turns out to be 2.21 times 10 to the minus 11 farads, or 22.1 picofarads. And so that was number 2. And last, we'll do number 3. This one is a little bit more work, but not tons more work. The potential difference between the plates is 150 volts, that's delta V. The electric field between the plates is 500,000 newtons per coulomb. And we have circular plates with a radius of 0.0250 meters. And we might put in a reminder here that area is pi r squared for our circle. So this one sort of feels like a mix and a match between the two ways to figure out capacitance. So we have some symbols where we could use Q over delta V. We have some symbols where we could do this. Why don't we see if we can figure out a way to put it together and find our answer. So I'm going to start with my top expression. C is equal to Q divided by delta V. And I'm sort of starting here because I know my potential. All right, so now what I want to do is ask if I know any of this information, could I figure out my Q? That's where I'd like to go next with this. Well, I remember that electric field is charge density divided by epsilon naught. That's our expression for finding electric field between the plates of capacitor. Charge density is charge divided by area. The area of each plate is pi r squared. Okay, so this pulls things together for me. I'd like to find my Q. I know E and R and epsilon naught and pi. So Q is equal to my electric field times pi r squared times epsilon naught. So I can pop this in for my Q and figure out my capacitance. And that capacitance turns out to be 5.79 times 10 to the minus 11 farads, which we could write as 57.9 picofarads if we wish. Yep.
So the question we did before this, and we were talking about like charge has no effect on capacitance.
Yep.
But if C equals Q over delta V,
Yep.
would charge and capacitance not be proportional?
Okay, that is a great question. Let's go back to that question.
Unless it's like a different charge, maybe that we're talking about in one situation than another.
Okay, you're thinking the right thoughts now.
Yeah.
But let's go back to it. I just want to get everybody finished with these notes first before we go back. So let's go back to what you asked about your expression for capacitance. So capacitance is equal to Q divided by delta V. That is absolutely correct, 100%. Our new capacitance will be when we double the charge. So our new capacitance, let's call that C prime. That's going to be our new charge, Q prime, divided by our new potential. Let's assume everything changes, and let's see if we can shake it out what the capacitance is. So let's deal with the charge first. We've doubled it, so it's 2 times the original charge over delta V prime. So let's remember that potential is electric field times distance. So we'll put that bit in. 2Q. My electric field, maybe that one changed, so I'm going to give that an E prime. But the distance between the plates certainly doesn't change. Okay, so I'm not going in tinkering with that plate separation. So D stays the same, so it has its symbol D. My electric field is sigma over epsilon naught. Sigma might have changed, so that gets a prime. Epsilon naught does not change, no prime on that one. Times d. So are we good here? Okay, let's remember what sigma is. Charge density is charge divided by area, Q prime. Area does not change because we're not changing the physical properties of that capacitor. Times d. Let's remember what we did to our charge. And we see that our two Q's cancel. A epsilon naught over D equals our original capacitance. So the thing that happened when you doubled the charge was that you doubled the electric field and you doubled the potential. Yeah, good question though. Okay, now we're going to go back to capacitors in a circuit. So like I said, any device you open up and look inside is going to be full of capacitors, which means when we put capacitors in a circuit, we have to hook them up. You have not done the circuits lab in your labs yet, is that right? Have you taken out like a box of resistors and wires and put those together yet? No, okay. So that's going to be coming and you're going to see about assembling circuits and how you connect things.
I think we did.
Some of us did.
Maybe
Yes.
Thursday did and Monday didn't?
Thursday did.
Yeah, okay. So Thursday kind of has seen about connecting things. Mondays we'll get to see it next time there's a lab on Monday. Yeah, does Monday have a lab? Anyway, you will see it. So we're gonna start to talk about how we put them together. And there are different ways to combine them. And the two ways we're gonna talk about first are gonna be series and parallel. People who did physics in high school probably remember lots about series and parallel capacitors. We have the same sort of connections here, different equations, but same idea about the connections. So we're gonna start with our easiest connection, which is capacitors in series. And when things are connected in series, they're just connected in a row. So they're all connected end to end. So if you wanted to see what that sort of looked like, you would take one wire and you would hook up the alligator clip to one end of the capacitor. You would take another wire to the other end. And then you would go from the end of that wire into a new capacitor, like that. And then out of that capacitor with a separate wire. So they're just all in a line. So that's how you connect something in series. They're all in a row from one end to the other end. So then the process of what happens, so here's three capacitors. They're all connected by wires in the middle in between. So they're all connected in a row in series. What happens in our charging process is that we hook up the battery. The positive charge comes out of the battery, flows through the circuit, hits the top plate, puts a positive charge here. That repels a positive charge from here. Positive walks away, which means that top plate remains, or the top plate is positive, the bottom plate is negative. That positive charge that got repelled hits the top plate of the next one, repels a positive charge from the bottom plate, leaving that one negative. That positive that got repelled hits the top plate of the third one, repels a positive from the bottom plate of the third one, leaving the bottom plate negative. So in that sense, the charge is going to flow, leaving the top plates positive and the bottom plates negative. We'll continue around the circuit until it's all charged up. If you think about it on a charge by charge basis, every time we get a positive here, we repel a positive here, which ends up here, which repels here, ends up here, repels, and goes back around. It means they all have to have the same charge. Okay? We can't have different amounts of charge on the plates. So when we have capacitors in series, every capacitor has the same charge. So that's something we know about capacitors in series. So the charges all have to be the same, so we could go on our diagram and we could label them all Q. Or you could say Q1 equals Q, Q2 equals Q, Q3 equals Q, or just label them all Q, but it all has to be the same regardless. Our battery supplies a certain amount of potential that we might call epsilon, or we might call delta V, it doesn't matter what notation we use. That potential would have to get split over the three capacitors. Okay? There's a certain amount of potential to put into the system, and it has to be distributed over the three. So if we had 100 volts, we can only put 100 volts out there. It might get distributed in different amounts, but whatever we distribute, it can't be more or less than 100. It's kind of a conservation of energy thing. So our battery supplies the potential. And that potential gets split or divided over all the capacitors. So each capacitor will have a potential delta V1, delta V2, delta V3. So because the potential of the battery is split, it means delta V is delta V1 plus delta V2 plus delta V3. So physically, that's what's going on with the capacitors. If we remember that capacitance C is equal to Q divided by delta V, then we know that delta V is going to be Q over C. So we could put that in our expression here. Delta V1 is going to be my charge divided by C1. Delta V2 is my charge divided by C2. Delta V3 is my charge divided by C3. So that gives me a way to know the total amount of potential put out by that battery. So good to hear. The next thing we can do physically, and frequently do in an analysis, is we can take out these three capacitors, so pop those out of the circuit. We could put in a new capacitor that we call C equivalent, an equivalent capacitor, and we could have it so that that new capacitor, if we pick exactly the right value, it will draw exactly the same amount of charge when connected to the same battery. Okay, so I can take out these three and put in an equivalent that would give me the same charge for the same potential. That's called an equivalent circuit. So from this picture to this picture is an equivalent circuit. And in my equivalent circuit, we replace C1, C2, and C3 by C equivalent. So that's one single capacitor with an equivalent capacitance. And that will have charge Q and potential same as the battery, delta V or epsilon. You probably did these in high school with resistors. Same deal with capacitors, works the same way. This equivalent capacitance, since it has charge Q and potential delta V, we can say that C equivalent is equal to charge divided by delta V. We're just using our relationship that we know. That means that delta V has got to be Q divided by C equivalent, Okay, so we can rearrange this and solve for delta V. We pop that in this equation down here. Delta V is Q divided by C equivalent. So they have to be the same result. If we divide both sides by Q, the result is that 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. And if we had more capacitors, we would just keep adding them until we got to the end. So we would add them until we had them all up. So this is an expression that gives us the equivalent capacitance for capacitors connected in series. Good. So, an interesting application of this, something I did not know until I taught about capacitors in this course, and I was looking up interesting examples. This explains how your touch screen works. So your phones and your iPads, they have a glass top, right? Underneath the glass screen, there's a couple of layers of a transparent material. Indium oxide is a common one, but there can be other ones as well. Those layers of indium oxide, one is a layer of strips that go up and down vertically like this. The other is a layer of strips that goes across horizontally like this, so they're crisscrossed. Every place they crisscross, you've got these two strips, it forms a capacitor. So underneath the glass screen, you've got a whole network of capacitors. And it's all very tiny, of course, right? So there's a whole lot of small capacitors. And then you go to touch your touch screen. Remember something we talked about human beings the other day? We're very pointy and we're full of charges. We have lots of electric fields around us. So we become the second half of a capacitor when we touch our screen. So your finger and the glass screen become a second capacitor. The circuitry inside can recognize that there's now been a change in capacitance because there's two capacitors in series. It can register that change in capacitance, and that's how it knows where you touched. So I think that's kind of neat. It's also sort of how keyboards work too, right? You press down on the key, you change the spacing, it registers a change in capacitance. So those capacitors, they're just everywhere.
Or if you get the light sensor keys, they work off of the break in the light.
Yep, all those things. That's cool. Okay, so let's do an example. I'm going to change these values here because I don't like them anymore. I want them to match what we did in our example where we calculated the three capacitances. So this one is going to be 12 picofarads. This one is going to be 22.1 picofarads, and this one's going to be 57.9. Okay, so those are now changed. We're asking what are the charge and the potential across each capacitor if the potential of the battery is 30 volts. So right off the top of our heads, let's remember that the charge on each capacitor is going to be the same. And the potential across each capacitor is going to be split, where the potential over all the capacitors is going to be split. So let's just make sure we kind of establish the things that we know. The first thing that we know is if we draw an equivalent circuit, so we would put in our battery with a potential of delta V, we would put in our equivalent capacitance, which we label C equivalent. We would know that that delta V equals the net charge on the capacitor plates, which is going to be the same here, 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 and here, all the same across the board, divided by the C equivalent. Okay, so that's one thing we know from our equivalent circuits. And then we also know that the potential across the first capacitor would be the charge divided by the first capacitance, and that's true for all the capacitors. when we write down these things, it kind of gives us a strategy to solve the problem. We know delta V, we know lots about the capacitances, so we could find C equivalent, which means we could find Q. After we find Q, we could come back and find all of those potentials, so that gives us a strategy for this problem. Let's find our C equivalent first, so we'll use our equation. 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. 1 over 12 picofarads plus 1 over 22.1 picofarads plus 1 over 57.9 picofarads. Put all that through the calculator, you get 0.146. Picofarads is in the denominator, so you might say picofarads to the minus 1. And to find your equivalent capacitance, you take the reciprocal of both sides. And we get an equivalent capacitance of 6.86 picofarads. If you don't like working in that picofarad unit, it's fine to put in times 10 to the minus 12 everywhere. You'll still get the same answer. That's no problem. Okay, so now I've got my equivalent capacitance. I can now come to this equation and find my charge. So Q is equal to delta V times C equivalent. 30 volts times 6.86 times 10 to the minus 12 farads gives me a net charge of 206 times 10 to the minus 12 coulombs, or 206 picocoulombs if you prefer. So there's my charge on each of those 3 capacitors, or the equivalent capacitance if I constructed that circuit. Questions? Okay, I think we have just enough time to find the potential across each of these capacitors. So delta V1 is equal to Q over C1. 206 times 10 to the minus 12 coulombs divided by 12 times 10 to the minus 12 farads gives me delta V1 is 17.1 volts. Delta V2 is going to be the same charge divided by 22.1 picofarads to get 9.3 volts. And my third potential is 206 picocoulombs divided by 57.9 picofarads to get 3.6 volts. And you might notice delta V1 plus delta V2 plus delta V3 equals 30 volts, as it should, right? So if you add them up, you can double check that you did all your calculations correctly. We are a couple of minutes early, but the next thing I want to do is start capacitors in parallel. So let's kind of start that as a solid chunk on Monday. So we'll just leave that there for today.